Hello there, and welcome to Nightfall Science. Tonight, we drift toward Alpha Centauri, the nearest star system beyond our Sun. Let your shoulders soften. Its distant light will remain steady while you rest. Let's begin. The nearest star system is not a single star, but a quiet family of three. Alpha Centauri appears to the unaided eye as one bright point in the southern sky. At such a distance, its separate lights blend together. A closer view reveals a more intricate arrangement. Alpha Centauri A and Alpha Centauri B form a close binary pair. They travel around a shared center of gravity, completing one orbit in roughly 80 years. Alpha Centauri A resembles the Sun in several important ways. It is a little larger and more massive, with a warm yellow-white glow. Alpha Centauri B is somewhat smaller and cooler. Its light carries a softer orange tint. The two stars approach and separate as their long orbit unfolds, like lanterns circling one another across a dark room. Far beyond this central pair lies Proxima Centauri. It is a small red dwarf, faint enough to remain invisible without a telescope. Proxima sits about 2/10 of a light-year from Alpha Centauri A and B. That gap is enormous by the standards of a planetary system. Yet the three stars move together through the galaxy, bound within the same broad stellar family. A spacecraft entering this system would not arrive at one simple destination. It would enter a landscape measured in light days and light months. The bright pair would occupy one region. Proxima would remain far away in another. Choosing a destination would therefore shape the entire mission. A path toward Proxima would not naturally pass close to Alpha Centauri A or B. The view from inside the system would also differ greatly from the familiar view on Earth. Alpha Centauri A and B could shine as brilliant neighboring suns. Proxima, despite being the closest destination, would appear much dimmer. The system would reveal its true size only after the spacecraft had already traveled between its widely separated regions. Even the closest stellar system is wider and more layered than its name suggests. What looks like one point from Earth is really a small celestial archipelago, with immense darkness lying quietly between its islands of light. 4 light-years is a distance that familiar measurements struggle to hold. Proxima Centauri lies about 4.25 light-years from the Sun. Alpha Centauri A and B sit slightly farther away, near 4.37 light-years. A light-year is not a measure of time. It is the distance light crosses during 1 year, moving at nearly 300,000 kilometers every second. 1 light-year equals roughly 9.46 trillion kilometers. Multiplying that distance by more than 4 produces a span of about 40 trillion kilometers. The number is so large that it becomes difficult to picture. Ordinary journeys offer little help. Oceans, continents, and even planetary distances are too small to serve as comfortable comparisons. The average distance between Earth and the Sun is 1 astronomical unit. Proxima Centauri is about 268,000 astronomical units away. If the distance from Earth to the Sun were represented by 1 small step, the journey to Proxima would require hundreds of thousands of similar steps. The planets would remain clustered near the beginning, while almost the entire path would stretch beyond them. Another scale makes the emptiness clearer. Imagine the Sun reduced to a small bead. Earth becomes a grain, moving only a short distance away. On that scale, Neptune remains nearby enough to fit within a room or garden. The next stellar system, however, would lie many kilometers from the bead, depending on the chosen scale. Even the sunlight reaching Earth has crossed only 8 light minutes. Neptune is generally measured in light hours. Alpha Centauri begins only after those familiar light minutes, and light hours have been repeated across more than 4 complete years. The difference is not a small step upward, it is an entirely new level of distance. This is the first great change in an interstellar journey. The solar system feels enormous while traveling among its planets. Yet from the perspective of Alpha Centauri, those planetary paths form only a tiny neighborhood around the Sun. The distance does not merely add more space to cross, it changes the meaning of travel itself. The route is not a longer version of a voyage to Mars or Jupiter. It is a passage across a gulf, where the departure system slowly becomes a star, and the destination remains a star for almost the entire way. Light itself needs years to carry news between the two systems. A signal leaving Earth travels at the fastest speed permitted by modern physics. It crosses the Moon's distance in a little more than 1 second. It reaches the Sun in about 8 minutes. It takes hours to reach the outer planets, depending on their positions. Yet the same signal requires more than 4 years to arrive at Alpha Centauri. This delay shapes every possible mission. A spacecraft near Proxima Centauri could send a message home, but Earth would not receive it until years later. A reply would require another 4 years to return. One simple exchange could therefore unfold across nearly a decade. Commands used in present-day spaceflight often depend on careful conversations between a spacecraft and controllers. Engineers receive data, study a problem, prepare instructions, and send them back. That pattern works across the solar system, even when the delay lasts minutes or hours. Across interstellar space, the same method becomes too slow for urgent decisions. An Alpha Centauri probe must therefore carry far more independence. It must recognize hazards, adjust its path, manage its power, and protect its instruments without waiting for immediate help. Its software becomes a distant form of judgment, built on Earth, but operating years beyond any direct conversation. Sending the signal is only part of the task. Radio waves and laser beams spread as they cross space. By the time a message reaches Earth, it may be extremely faint. Large receivers must separate it from background noise. A small probe may gather remarkable images, yet returning those images could take months or years of careful transmission. The delay also changes the emotional rhythm of discovery. Images captured during a close passage would not appear on Earth in real time. The spacecraft might already be far beyond the system when its first detailed observations finally arrive. Each packet of data would be an old message from a machine continuing through the dark. Interstellar communication is therefore not silent, but deeply patient. Earth and spacecraft remain connected by light, yet every word crosses a distance wide enough to contain years. The destination never waits in one fixed place. Alpha Centauri moves through the Milky Way, just as the Sun does. Its stars also orbit within their own system. Proxima Centauri shifts against the distant background, while Alpha Centauri A and B continue their 80-year dance. A spacecraft cannot simply aim at the place where the system appears at launch. Mission planners must predict where the chosen star will be when the probe arrives. For a voyage lasting decades, that future position may differ greatly from its present position. The spacecraft must cross not only distance, but time, meeting a moving target after both systems have continued along their galactic paths. This resembles throwing a small object toward a boat far beyond the horizon. The throw must account for the boat's motion during the entire flight. Interstellar navigation is far more exacting because the crossing may last a human lifetime and the final target may be a planet moving around a star. The stars used for navigation also change subtly as the spacecraft travels. From Earth, constellations appear almost fixed because the stars are extremely distant. From a point far outside the solar system, nearby stars begin to shift against the background. The familiar sky gradually changes its geometry. The spacecraft must determine its position without relying only on instructions from Earth. Star cameras, precise clocks, radio measurements, and perhaps observations of pulsars may help it estimate where it is. Small corrections made early can prevent enormous errors later. A tiny angular mistake, extended across trillions of kilometers, can grow into a miss measured in astronomical units. Reaching a planet makes the calculation even more delicate. The planet continues circling its star while the probe approaches. A fast spacecraft may cross the entire planetary system in hours or days. Its instruments must turn toward the correct location before the target passes quietly out of view. The path to a star is therefore not a straight line drawn once on a map. It is a living prediction, revised through careful observation as the spacecraft and its destination continue moving through the galaxy together. A Voyager-like spacecraft would need tens of thousands of years to arrive. Voyager 1 is one of the fastest objects ever sent away from the Sun. It escapes the solar system at roughly 3.5 astronomical units each year. That speed is remarkable by human standards. It allows the spacecraft to cover hundreds of millions of kilometers annually, while continuing its quiet passage through interstellar space. Yet Alpha Centauri remains far beyond the scale of Voyager's journey. At a speed near 17 kilometers per second, a spacecraft would need roughly 75,000 years to cross the distance to Proxima Centauri, assuming it traveled in the correct direction. Voyager 1 does not point toward Proxima, but its speed offers a useful comparison. 75,000 years reaches deeper into time than the whole span of recorded history. It is longer than the age of cities, agriculture, and written language combined. A probe launched at that pace would outlive nations, languages, and perhaps entire branches of technology before reaching the neighboring system. Its survival would become a question unlike any present mission. Materials slowly change, radiation alters electronics, microscopic impacts wear exposed surfaces, power sources fade, mechanical parts remain vulnerable even when they rarely move. A machine designed for such a crossing would need to preserve itself across a duration normally associated with geology and human prehistory. Communication would face a similar challenge. The people who launched the spacecraft would never see its arrival, neither would their children, or any ordinary chain of descendants. The mission would belong to a civilization rather than a generation. Instructions, maps, and scientific goals might also lose their original context. Future observers would need to understand technology built in a distant age. The spacecraft would become both an instrument and an artifact, carrying the engineering choices of people separated from its arrival by thousands of generations. Voyager reveals both human achievement and interstellar scale. It has crossed the heliopause and entered the space between stars, yet it has traveled only a tiny fraction of the distance to the next system. The neighboring stars are close on a galactic map, but current spacecraft move through that map with the pace of drifting dust. The fastest spacecraft record does not translate into an easy interstellar crossing. Parker Solar Probe reaches about 430,000 miles per hour during its closest passes around the Sun. It is the fastest human-made object ever measured. At first glance, such speed seems to shorten the journey to Alpha Centauri dramatically. A simple division suggests a trip lasting several thousand years rather than tens of thousands. But Parker's record occurs under special conditions. The spacecraft falls deep into the Sun's gravity and sweeps rapidly around it near perihelion. Its speed is tied to that close solar orbit. Parker is not leaving the solar system at 430,000 miles per hour, and a large spacecraft cannot simply copy its motion and continue outward with the same velocity. An interstellar vehicle must gain tremendous speed while also departing in the correct direction. If it plans to stop near its destination, it must later remove nearly the same speed. Acceleration solves only half the problem. Deceleration requires another source of energy, another propulsion method, or a carefully designed interaction with the destination system. Without braking, a probe would receive only a brief encounter. At 1/5 of light speed, it could cross a distance equal to Earth's orbit in less than an hour. Years of travel would lead to a passage measured in moments. Cameras and sensors would need to gather their observations with extraordinary speed. Speed also changes the character of small particles. A grain of dust drifting harmlessly through ordinary space carries much greater impact energy when struck at a substantial fraction of light speed. Protective shielding, detection systems, and perhaps a narrow forward profile become central parts of the design. The energy demand rises rapidly as the desired speed increases. Moving a tiny probe is far easier than moving a crewed ship. Every additional kilogram requires more energy to accelerate, more protection during flight, and more energy to slow at the far end. The record set near the Sun remains a beautiful demonstration of motion. Yet interstellar travel asks for something different. Sustained outward speed, extraordinary efficiency, long endurance, and a gentle arrival after years among the stars. The journey begins not with one impossible leap, but with many quiet problems that must all be solved together. Ordinary chemical rockets carry too much of their own journey with them. Almost every spacecraft launched from Earth relies on chemical propulsion. A fuel and an oxidizer react inside a chamber. Hot gas escapes through a nozzle. The gas moves backward, and the spacecraft moves forward. This simple exchange has carried astronauts to the Moon and probes throughout the solar system. Chemical rockets work beautifully when the required speed remains within familiar limits. The difficulty appears when a mission demands much larger changes in velocity. A rocket must carry fuel to accelerate its payload. It must also carry fuel to accelerate the remaining fuel. Adding propellant therefore adds mass, which creates a need for still more propellant. This relationship is described by the Tsiolkovsky rocket equation. The equation connects a rocket's change in velocity with the speed of its exhaust and the ratio between its initial and final mass. The result grows logarithmically. Each additional increase in speed requires a rapidly expanding mass ratio. For interstellar travel, the problem becomes overwhelming. A conventional rocket attempting to reach even a modest fraction of light speed would require a launch mass far beyond anything practical. If the spacecraft also carried fuel for braking, The departure stage would need to accelerate the arrival fuel as well. The design begins to resemble a stack of fuel tanks carrying other fuel tanks across the dark. Staging helps ordinary rockets. Empty tanks and engines are released after their work is complete. Yet even many stages cannot easily bridge the gap between planetary and interstellar speeds. Chemical reactions contain only a limited amount of energy per kilogram. Their exhaust velocities remain far below the speeds required for a journey lasting decades rather than millennia. This does not make chemical propulsion unimportant. Rockets may still lift components from Earth, assemble vehicles in orbit, or send them toward a more powerful propulsion system. They could serve as the opening movement of a much longer journey. The chemistry that carries machines away from Earth is one of humanity's finest tools. Yet between the Sun and Alpha Centauri, even a great rocket begins to seem like a gentle spark beside an ocean. Interstellar speed requires energy on a planetary scale. The energy of motion depends on both mass and velocity. At everyday speeds, the relationship is described by 1/2 of the mass multiplied by velocity squared. Doubling speed, therefore, requires 4 times as much kinetic energy. Increasing speed tenfold requires 100 times as much. This square relationship becomes central to interstellar travel. A small probe moving at 1% of light speed travels at roughly 3,000 kilometers per second. That is already far faster than any spacecraft launched from Earth. At 10% of light speed, the same probe carries 100 times more kinetic energy. A spacecraft with a mass of 1,000 kilograms would appear small beside many modern satellites. Accelerating that mass to 10% of light speed would require an immense quantity of energy. The ideal kinetic energy alone would reach hundreds of petajoules. Real propulsion systems would need considerably more because no engine converts stored energy into motion with perfect efficiency. The difficulty grows with the spacecraft. A crewed vehicle needs living space, power systems, shielding, supplies, instruments, engines, and redundancy. Each protective layer adds mass. Every added kilogram must be accelerated during departure and perhaps slowed again at the destination. Energy storage creates another challenge. Chemical fuels cannot hold enough energy for such speeds without impossible mass ratios. Nuclear fission contains far more energy per kilogram. Fusion offers more still. Matter-antimatter reactions would theoretically release an even greater fraction of mass as usable energy. Yet producing, storing, and directing antimatter in large quantities remains far beyond current engineering. Heat must also be managed. An engine may release enormous energy, but only part becomes forward motion. Waste heat must leave through radiators. In space, heat cannot flow into surrounding air. It escapes mainly as infrared radiation, requiring large surfaces and careful temperature control. The spacecraft must therefore be more than a fast machine. It must be an energy system of extraordinary efficiency, holding power, motion, heat, and mass in delicate balance. Across interstellar space, distance is only the visible problem. Quietly beneath it lies the deeper requirement: enough controlled energy to move a small world between the stars. Nuclear propulsion could shorten the journey without making it simple. Atomic nuclei contain far more stored energy than chemical bonds. This difference makes nuclear propulsion attractive for ambitious spaceflight. Several designs have been studied, ranging from nuclear-heated rockets to engines powered by fission fragments or fusion reactions. A nuclear thermal rocket uses a reactor to heat a light propellant, usually hydrogen. The hot gas expands through a nozzle and creates thrust. Because the reactor supplies the heat, the exhaust can leave faster than gases produced by ordinary chemical combustion. Such engines could improve travel within the solar system. Even nuclear thermal propulsion, however, remains too slow for a practical voyage to Alpha Centauri. More advanced concepts attempt to use nuclear reactions more directly. Fusion propulsion would combine light atomic nuclei, releasing energy similar to the process that powers stars. Project Daedalus, studied by the British Interplanetary Society during the 1970s, explored an uncrewed fusion probe to Barnard's star. Its design imagined tiny pellets containing deuterium and helium-3. Electron beams would ignite these pellets one after another. Each pulse would produce hot plasma, which magnetic fields would direct behind the spacecraft. The proposed vehicle was enormous. It would have used tens of thousands of tons of fuel and accelerated for several years. Its planned cruising speed approached 12% of light speed. Even then, the probe was designed for a flyby rather than a gentle stop. A later study called Project Icarus revisited the idea with newer materials and engineering knowledge. These projects are not finished spacecraft plans. They are detailed thought experiments, revealing what a physically plausible interstellar engine might demand. Fusion fuel presents practical difficulties. Deuterium is available, but helium-3 is rare on Earth. The ignition system must create controlled pulses reliably for years. The engine must survive repeated exposure to intense energy while remaining precisely aligned. A fusion craft would also be built on a scale unlike ordinary probes. It might resemble a moving industrial structure, assembled beyond Earth and tested across the outer solar system. The stars demonstrate that fusion can shine for billions of years. The quieter challenge is learning to hold a small part of that process and shape it into a steady road through space. A laser sail could leave most of its engine at home. A spacecraft normally carries both its payload and its source of propulsion. A light sail changes this arrangement. Photons have no rest mass, yet they carry momentum. When light reflects from a surface, it produces a small pressure. A sufficiently powerful beam can therefore push a very light spacecraft. Breakthrough Starshot is a research initiative examining this possibility. Its central idea involves tiny spacecraft attached to thin reflective sails. A large array of lasers on or near Earth would illuminate each sail for several minutes. The beam would provide intense acceleration, potentially raising the craft to a significant fraction of light speed. Because the energy source remains near Earth, the probe does not need to carry massive fuel tanks. The spacecraft could be extremely small, perhaps only a few grams for its central electronics. Cameras, sensors, communications equipment, and navigation systems would all need to fit onto a device, sometimes described as a star chip. The sail itself would need remarkable properties. It must be very light, strongly reflective, and resistant to heating. Even a tiny fraction of absorbed laser energy could damage such a delicate surface. The sail must also remain stable within the beam. If it tilts or wrinkles, the force may push it away from the desired path. The laser array presents a different scale of engineering. Thousands or perhaps millions of emitters would need to act as one coherent system. Atmospheric turbulence could distort a beam sent from Earth. Adaptive optics might correct some of that distortion, while a space-based array would avoid the atmosphere but become harder to construct. A probe moving near 20% of light speed could reach the Alpha Centauri system in roughly 2 decades. Yet the encounter would be brief. The craft would pass through the system without carrying fuel to stop. Its instruments would need to collect data quickly and transmit it across more than 4 light-years using very little power. The concept replaces one large spacecraft with many tiny messengers. Some may fail, while others continue. Together they could form a quiet stream of artificial dust crossing the distance between neighboring suns. The engine remains behind, the sail moves ahead, and a beam of light becomes a bridge between worlds. The space between stars is thin, but it is not completely empty. Interstellar space contains gas, dust, magnetic fields, cosmic rays, and particles flowing from distant astrophysical events. The density is extremely low. In many regions, only a fraction of an atom occupies each cubic centimeter. A spacecraft moving slowly would pass through this material with little immediate effect. At interstellar speeds, the same particles become more important. The spacecraft does not need to encounter a fast-moving grain. Its own velocity supplies the relative motion. A hydrogen atom, meeting a craft traveling at a large fraction of light speed, can strike with energy resembling energetic radiation. Larger dust grains are much rarer, but their impacts carry greater energy. A particle smaller than sand may contain little energy while drifting gently through space. When struck at tens of thousands of kilometers per second, it releases its energy across a tiny area and a very short moment. The forward surface of an interstellar probe therefore needs protection. One proposal uses multiple thin shielding layers, separated by empty gaps. The first layer breaks an incoming particle into plasma and fragments. Later layers spread and absorb the expanding material. This general approach resembles a Whipple shield, already used to protect spacecraft from small orbital debris. An interstellar shield may also use ice, graphite, ceramics, metals, or carefully arranged sacrificial materials. A thick forward barrier adds mass, which requires more propulsion energy. A thin barrier saves mass but provides less protection. The design must find a balance between endurance and speed. Some concepts place a cloud of fine particles ahead of the spacecraft. The cloud would meet larger grains first, reducing their effect before they reach the vehicle. Other ideas involve magnetic or electric fields that redirect charged particles. Neutral dust, however, does not always respond conveniently to such fields. The exact environment along the route is not fully known. Astronomers can estimate average gas and dust densities, but a narrow spacecraft path may contain local variations. Precursor probes could help map the space ahead before a larger mission begins. The darkness between stars is not a perfect vacuum. It is a faint cosmic weather, almost empty by earthly standards, yet meaningful to anything moving quickly enough to notice every grain. Radiation slowly changes a spacecraft during the long crossing. Earth's atmosphere and magnetic field provide a broad shelter from much of the space environment. Beyond the heliosphere, a spacecraft loses part of that familiar protection. Galactic cosmic rays arrive from many directions. They include atomic nuclei, accelerated to high energies by events such as supernova remnants. These particles can pass through materials and leave trails of ionization. In electronic components, they may alter stored information or cause temporary errors. A single energetic particle can change the state of a memory bit. More sustained exposure can gradually damage circuits and sensors. Modern spacecraft already prepare for this environment. Radiation-hardened electronics use larger, more robust components. Important computers may operate in groups, comparing their results. Memory can include error-correcting codes. Systems can restart after faults and isolate damaged components. An interstellar probe must continue this protection for decades, centuries or longer, depending on its speed. It cannot depend on regular repair. Redundant components may remain dormant until needed. Software must detect its own failures and choose replacements without guidance from Earth. Materials also change under radiation. Polymers may become brittle. Optical surfaces can darken. Solar cells lose efficiency. Lubricants and adhesives may degrade. Even systems with no moving parts remain subject to slow atomic damage. The probe's own speed adds another source of radiation. Interstellar hydrogen striking the forward shield at high velocity can produce secondary particles. The shield protects the interior, but the collision energy must still be absorbed and carried away. Very small probes face particular difficulty because they have little room for shielding. Large vehicles can place equipment behind water, fuel, or thick structural layers. A gram-scale probe must depend on careful materials, redundancy, and a mission short enough for its systems to survive. Radiation damage is rarely dramatic. It is an accumulation of tiny changes, each one nearly invisible. The machine slowly ages while no planet, moon, or station lies nearby. A successful interstellar craft must therefore carry the ability to endure silence. Its finest achievement may be simply remaining itself, while the sun grows faint behind it. A spacecraft crossing interstellar space must carry power through years of darkness. Solar panels work well near the sun. Light strikes their surfaces and releases electric current. Many spacecraft depend on this steady source of energy. Yet sunlight weakens with the square of the distance. Twice as far from the sun, a panel receives only 1/4 as much light. 10 times farther away, it receives 1/100th. Beyond the outer planets, solar power becomes increasingly difficult. A probe traveling toward Alpha Centauri would soon leave the region where ordinary panels remain useful. For most of the journey, it would drift between stars, surrounded by light too faint, and scattered to support its systems. Present deep space missions often use radioisotope thermoelectric generators. These devices contain radioactive material, commonly plutonium-2. As the material naturally decays, it produces heat. Thermocouples convert part of that heat into electricity. Voyager 1 and Voyager 2 have used this method for decades. Their power steadily declines as the radioactive material cools and the electrical components age. Engineers gradually switch off instruments to preserve the remaining energy. An interstellar mission would face the same process across a much longer interval. Other radioactive isotopes could provide power for different durations. A long-lived isotope releases its energy slowly, producing less power at any given moment. A shorter-lived isotope supplies more heat but fades sooner. Choosing a source means balancing intensity against endurance. A larger probe might carry a compact nuclear fission reactor. Unlike a radioisotope generator, a reactor controls a chain reaction and can produce much greater electrical power. Reactors also require shielding, cooling, control systems, and long-term reliability. The craft may conserve energy By sleeping through much of the crossing, most instruments could remain inactive, while a small computer watches the vehicle's condition. At planned intervals, the system would wake, check its course, inspect its components, and then settle again. Near the destination, the probe would need more power. Cameras, radar, spectrometers, navigation sensors, and communication equipment may all operate together. Energy stored slowly during the cruise could be released during the brief encounter. The journey takes place through darkness, but the spacecraft must preserve a quiet ember within itself, waiting years for the moment when another star fills its instruments with light. Long sleep may be easier for machinery than continuous wakefulness. A spacecraft does not need to remain fully active during every moment of an interstellar crossing. Most of the route contains no planet, moon, or nearby object to examine. The craft may spend years passing through nearly uniform space. Operating every instrument continuously would consume power and wear components without producing much new information. Engineers already use forms of spacecraft hibernation. During these periods, many systems shut down. Heaters, clocks, and a small control computer remain active. The spacecraft wakes at scheduled times or after detecting an unusual condition. The New Horizons probe used hibernation during parts of its long journey toward Pluto. This reduced demands on its systems and lowered the workload of the mission team. Rosetta also entered a deep hibernation while traveling far from the Sun, later awakening before its encounter with Comet 67P. An interstellar probe would require a far deeper form of sleep. Its dormant period might last months or years between checkups. The craft would need to wake without receiving a command from Earth. It would test its memory, compare its clocks, inspect its power supply, and determine whether its path remained correct. Dormant electronics can still age. Radiation continues to pass through the spacecraft. Tiny electrical charges can accumulate. Materials expand and contract as temperatures change. A component that worked at departure may not respond after decades of silence. Redundancy offers one answer. Several computers can store the same instructions. Some may remain unused until later in the mission. If the primary system fails, another can awaken and continue its work. Important information can be copied into different types of memory, so that one form of damage does not erase everything. The software also needs a careful understanding of time. A missed wake-up could allow the spacecraft to pass its destination in silence. Multiple clocks, based on different technologies, could compare their measurements and correct gradual drift. Hibernation transforms the journey into a sequence of brief moments. The probe wakes beneath a slightly different sky, listens to its own machinery, adjusts its path, and returns to stillness. Across decades of travel, the spacecraft may experience the voyage not as one continuous crossing, but as a quiet chain of awakenings between the stars. Precise clocks become navigation instruments far from Earth. Timekeeping is essential to spaceflight. A spacecraft determines distance by measuring how long signals take to travel. It calculates velocity by observing changes in signal frequency. It predicts its future position by combining these measurements with a precise record of time. Near Earth, ground stations provide much of this information. Large antennas send radio signals toward a spacecraft and receive its reply. The known travel time allows controllers to estimate the spacecraft's distance. Changes caused by the Doppler effect reveal whether it is approaching or receding. Across interstellar space, signals take years to arrive. Earth can still track the probe, but corrections based on those measurements become very old by the time they return. The spacecraft benefits from carrying its own highly stable clock. Atomic clocks measure time using the natural frequencies of atoms. These frequencies are far more regular than the motion of mechanical parts. NASA's Deep Space Atomic Clock demonstrated that a compact atomic clock could operate aboard a spacecraft with exceptional stability. A future interstellar probe might combine an atomic clock with observations of stars and pulsars. Pulsars are rapidly rotating neutron stars that emit beams of radiation. Some produce pulses with remarkable regularity. By measuring the arrival times of signals from several pulsars, a spacecraft could estimate its position in space. This method resembles celestial navigation on Earth. Sailors once compared the measured positions of stars with accurate clocks. An interstellar craft could perform a related calculation using some of the galaxy's most regular natural beacons. The clock must remain stable through radiation, temperature changes, and long periods without maintenance. Even a tiny error can grow important over decades. If a clock loses 1 second, a light-based distance measurement shifts by nearly 300,000 kilometers. Navigation would not depend on one instrument alone. Star trackers, gyroscopes, radio signals, optical observations, and onboard clocks would check one another. The spacecraft would build its location from several quiet agreements. Far from every planet, time itself becomes part of the map. Each precise second helps the probe understand where it is within the wide geometry of the stars. Sending photographs home may be harder than taking them. A camera near Alpha Centauri could capture extraordinary views. It might resolve the surfaces of planets only as tiny points, yet measure their colors, atmospheres, clouds, and temperatures. It could photograph the neighboring stars from a position no Earth-based telescope can occupy. Collecting this information requires sensors, stable pointing, and enough time near the target. Returning it to Earth creates a separate challenge. The probe must transmit across more than 40 trillion kilometers, with a power source small enough to survive the journey. Radio communication spreads energy across a widening region. Even a carefully directed antenna produces a beam that grows with distance. By the time it reaches Earth, the signal may be fainter than natural radio noise from space and from human technology. A laser can form a narrower beam. Optical communication therefore offers higher data rates for a given amount of transmitted power. Yet a narrow beam must point with extraordinary precision. A tiny angular error could cause the light to miss Earth completely. The receiving station must also know when and where to listen. Large telescopes may gather individual photons from the probe and identify patterns within them. Several observatories could combine their observations. Receivers in space would avoid clouds and atmospheric turbulence. Small probes face a strict energy budget. They may store data during the encounter and transmit it slowly afterward. A photograph could be divided into many packets. Error-correcting codes would allow Earth to reconstruct information, even when some packets arrive damaged or incomplete. Data compression would help, but excessive compression could erase subtle scientific details. The mission must choose which information matters most. A few carefully selected images may be more valuable than a large collection that cannot be returned. The transmission could continue for months or years as the probe moves beyond Alpha Centauri. Its signal would grow weaker with distance, while Earth's instruments patiently gathered each fragment. The first close image of another stellar system may not arrive as one brilliant picture. It may assemble slowly, pixel by pixel, from a whisper of light traveling home through the dark. A fast flyby turns decades of travel into a few hours of observation. A probe moving at 20% of light speed covers roughly 60,000 kilometers every second. That speed could bring it to Alpha Centauri in a little more than 20 years. Yet the same speed makes the encounter extremely brief. The distance between Earth and the Sun is about 150 million kilometers. At 20% of light speed, a spacecraft crosses that distance in roughly 42 minutes. A planetary system that took decades to reach could pass through the probe's useful field of view during a single day. The spacecraft cannot pause to reconsider its observations. Light from the target reaches its cameras, instruments make measurements, and the desired world quickly falls behind. Commands from Earth are impossible during this interval because they require more than 4 years to arrive. Every observation must be planned before the probe reaches the system. The craft needs to identify stars and planets by itself. It must choose exposure times, turn its instruments, avoid pointing too near a bright star, and store the resulting data. Photographing a planet during such a passage resembles photographing a distant bird from a rapidly moving train. The target begins as a faint point. It grows slightly larger, crosses the best viewing position, and then recedes. There may be no second opportunity. A group of probes could improve the result. They might arrive at different times or follow slightly different paths. One could observe a planet's illuminated side while another studies its night side. Several small failures would not end the entire mission. The probes could also begin observations long before arrival. As the system grows brighter, they could refine the planet's orbits and adjust their pointing. After passing through, they could continue watching the stars from behind, gaining another perspective. A flyby mission offers speed at the cost of time near the destination. It reaches the neighboring system within a human lifetime, but does not truly remain there. After years of almost motionless stars, the entire destination opens and closes like a quiet window, giving the spacecraft only moments to gather the light it crossed an ocean to find. Stopping at Alpha Centauri may require as much effort as reaching it. Acceleration is often treated as the central challenge of interstellar travel. A spacecraft must somehow gain enough speed to cross several light years. Yet a vehicle arriving at that speed will continue through the system unless another force slows it. Ordinary spacecraft use rockets for braking. They turn their engines forward and burn fuel, reducing their velocity. An interstellar craft carrying its braking propellant must accelerate that propellant from the beginning of the mission. This increases the vehicle's departure mass and the energy required to launch it. A laser sail pushed from the solar system faces a similar problem. The laser beam can accelerate the sail while it remains close enough to the array. Once the craft reaches Alpha Centauri, the original beam is far behind. Unless another laser already exists at the destination, the probe cannot use the same method in reverse. Several possible solutions have been proposed. A magnetic sail could create a large magnetic field that interacts with charged particles in the interstellar medium. Each interaction would remove a tiny amount of momentum. Over a long distance, the accumulated effect might slow the spacecraft. An electric sail uses charged tethers rather than a large magnetic loop. It could interact with protons in stellar winds. Near the destination star, the stronger flow of charged particles may provide additional braking. A reflective sail might also use light from Alpha Centauri itself. The sail would approach the star at a carefully chosen angle. Radiation pressure and gravity could bend its path and reduce its speed. The craft might then redirect toward another star or planet within the system. These methods require enormous precision. A braking sail must deploy correctly after decades in storage. It must survive heat near the star and maintain the right orientation. Arriving too quickly or at the wrong angle could leave insufficient time to slow. Stopping also lengthens the mission. A craft designed only for a flyby can devote almost all its resources to acceleration and observation. An orbiter must reserve mass and complexity for arrival. Reaching another star is a triumph of motion. Remaining there is a quieter achievement, asking the spacecraft to surrender the speed that carried it across the dark. An interstellar spacecraft must learn to make decisions without Earth. Modern probes receive detailed instructions from mission controllers. Engineers study telemetry, prepare command sequences, and send them across space. This works well when communication delays are measured in seconds, minutes, or even hours. Near Alpha Centauri, every signal requires more than 4 years to reach Earth. The spacecraft cannot pause while a question travels home and an answer returns. It must recognize events, select observations, and respond to changing conditions by itself. Its onboard computer becomes more than a scheduler. It becomes a quiet mission controller carried between the stars. NASA has already tested early forms of this autonomy. Deep Space One carried software called Remote Agent. During a demonstration in 1999, the system planned activities, operated spacecraft components, and responded to simulated faults with limited direction from Earth. It showed that a machine could receive broad goals rather than a complete sequence of individual commands. An Alpha Centauri probe would require a far more advanced descendant of this technology. It might compare images to stored star maps and identify unfamiliar objects. It could distinguish a planet from a background star by observing motion over time. During arrival, it might decide which target deserves the greatest attention. The system must also understand its own limits. A camera could become overheated. A memory unit could begin returning errors. A navigation sensor might disagree with the others. The software would need to isolate the problem, protect the remaining instruments, and continue with a revised plan. Artificial intelligence could help classify images and detect unusual patterns, yet reliability matters more than creativity. Every decision must remain understandable enough for engineers to test before launch. A machine that improvises too freely could waste energy or point an instrument in the wrong direction during the brief encounter. The probe would carry decades of human preparation inside its software. Astronomers, engineers, and programmers would shape the rules long before the spacecraft reached its destination. When the neighboring stars finally fill its cameras, no voice from Earth can guide the moment. The spacecraft must quietly remember what it was built to seek. Redundancy allows one spacecraft to contain several possible futures. No machine operates forever without change. A circuit can fail, A sensor can drift. Radiation can alter stored information. A switch may stop responding after remaining unused for many years. On Earth, damaged equipment can be inspected and repaired. An interstellar probe must continue without nearby hands. Spacecraft already use redundant systems to prepare for this possibility. Two computers may be capable of controlling the same mission. Several sensors may measure the same quantity. Electrical paths can be rearranged so that power avoids a damaged component. Fault protection software watches for signs that something has moved beyond its expected limits. It may place the spacecraft into a safe configuration, reduce power use, and point the communication antenna toward Earth. In the solar system, engineers can later study the problem. Near Alpha Centauri, the probe must perform much of that recovery alone. Voyager 2 provides a smaller example. In 2020, an onboard fault protection routine responded when two relatively power-hungry systems operated at the same time. The spacecraft protected itself while engineers worked across billions of kilometers to restore normal operations. An interstellar design could carry several dormant computers. The primary computer might operate during departure. Another could remain electrically isolated through most of the crossing, protected from gradual wear. It would awaken only if the first system failed or when the destination approached. Important instructions could be stored in several forms of memory. Error-correcting codes would identify and repair altered bits. Periodic checks could compare duplicate copies and replace damaged information with an intact version. Redundancy adds mass, however. Every spare computer, cable, and power converter requires energy to accelerate. Designers must decide which components deserve duplicates and which risks remain acceptable. A fleet of small probes offers another kind of redundancy. Instead of placing the entire mission inside one machine, the mission can be divided among many. Some may lose communication or miss their planned paths, while others preserve the scientific goal. The probe survives not because every part lasts forever, but because it carries more than one way to continue. Within one small craft, several quiet versions of the mission wait for their turn. The cold of deep space does not remove the problem of heat. Interstellar space is often described as extremely cold. The background glow of the universe has a temperature only a few degrees above absolute zero. Yet a spacecraft does not instantly become that cold. Temperature depends on how quickly it gains energy and how quickly it releases energy. Computers, batteries, transmitters, and nuclear power sources all produce heat. With no surrounding air, that heat cannot leave through convection. It must move through the spacecraft by conduction and then radiate away from an exposed surface. Radiators provide this path. They are designed to emit infrared energy toward open space. Their size and orientation help determine how much heat the spacecraft can release. During periods of high activity, instruments and transmitters may create more warmth, requiring a larger radiating area. Other components need protection from becoming too cold. Batteries and electronics operate only within particular temperature ranges. Multi-layer insulation slows the movement of heat. Electric heaters warm sensitive equipment. Small radioisotope heater units can provide steady warmth from natural radioactive decay without using the spacecraft's limited electricity. The balance changes during the mission. Near the sun, the craft may need to reject heat from sunlight and propulsion systems. During the long cruise, most equipment may be asleep, producing very little warmth. Near Proxima Centauri, the probe again enters a stronger field of starlight. A fixed radiator designed for one stage may work poorly during another. Louvers, heat pipes, variable surfaces, and adjustable radiator panels could help the spacecraft adapt. Yet moving mechanisms must still operate after years of silence. Tiny probes face an especially delicate balance. They have little mass to store heat and little surface area available for separate thermal systems. A brief laser pulse during departure may heat a light sail intensely, while the later cruise offers almost no external warmth. Space may appear cold and still, but every functioning spacecraft carries an internal climate. Its instruments survive inside a carefully maintained island of temperature, drifting between two distant suns. Proxima Centauri is a small star with a restless surface. Red dwarfs are the most common stars in the Milky Way. They are cooler, dimmer, and less massive than the Sun. Their modest size allows them to consume nuclear fuel very slowly. Some may continue shining for trillions of years, far longer than the present age of the universe. Proxima Centauri belongs to this broad family. It contains only a small fraction of the Sun's mass and gives off much less visible light. From a nearby planet, its glow would appear warmer in color, leaning toward red and infrared wavelengths. Its faint appearance does not mean that it is always quiet. Magnetic fields twist through the star's outer layers. When stored magnetic energy is suddenly released, Proxima produces flares. These events can brighten the star across radio, visible, ultraviolet, and X-ray wavelengths. Astronomers observed one especially energetic flare during a coordinated campaign in 2019. Several telescopes watched Proxima across different parts of the electromagnetic spectrum. The event rose and faded quickly, revealing how much the star can change within a short interval. A probe approaching the system would study this activity directly. Its instruments could measure charged particles, magnetic fields, ultraviolet light, and radio emission. These observations would show how the star shapes the space surrounding its planets. The spacecraft itself must also account for the changing environment. Sensitive detectors may need protective observing modes during strong events. Electronics require shielding. Arrival plans may include flexible schedules so that important planetary measurements do not coincide with an unusually bright flare. Several probes arriving at different times would provide a fuller picture. One might encounter a calm interval. Another could observe a period of greater activity. Together, their measurements would reveal patterns that a single passage might miss. Proxima's flares are not signs of a star behaving incorrectly. They are natural expressions of a small magnetic sun. Around this dim red light, space changes from hour to hour, breathing softly with the motion of an active star. Proxima Centauri b completes an entire year in only 11 days. The planet known as Proxima b was announced in 2016. Astronomers detected it through the radial velocity method. They measured a gentle repeated motion in Proxima Centauri as the gravity of the unseen planet pulled the star slightly forward and backward. Proxima b takes about 11.2 Earth days to complete one orbit. Its average distance from the star is roughly 0.048 astronomical units, only about 5% of the distance between Earth and the Sun. It travels much closer to Proxima than Mercury travels to the Sun. Yet Proxima Centauri produces far less energy than the Sun. The planet's close orbit therefore places it within the star's traditional habitable zone. This is the region where temperatures might permit liquid water if the planet has a suitable atmosphere and surface. Radial velocity measurements provide a minimum mass close to that of Earth. The planet is probably rocky, although no telescope has yet photographed its surface. Its radius, atmosphere, oceans, and magnetic field remain uncertain. Because Proxima b orbits so close to its star, tidal forces may have altered its rotation. One possible state is synchronous rotation. In that arrangement, one hemisphere continually faces the star, while the opposite hemisphere remains turned away. The Moon keeps a similar orientation toward Earth. Another possible state is a resonance in which the planet rotates a fixed number of times during several orbits. Mercury, for example, rotates 3 times for every 2 journeys around the Sun. Proxima b's exact rotation is not yet known. A synchronously rotating world would have no ordinary sunrise or sunset across most of its surface. The star would remain fixed in the sky. One side would rest beneath constant reddish daylight. The other would remain beneath a long, unbroken night. Between them would lie a wide region of permanent twilight, where the star sits close to the horizon. Winds and oceans, if present, could carry warmth across these hemispheres. On Proxima b, an entire year passes in less than 2 Earth weeks, while one quiet afternoon may continue without end. A habitable zone orbit does not guarantee a habitable world. The habitable zone is a useful starting point. It describes the range around a star where a rocky planet might maintain liquid water on its surface. The calculation depends mainly on the star's energy and the planet's orbital distance. It does not reveal whether the planet actually possesses water. It does not confirm an atmosphere, a magnetic field, or a stable climate. Venus, Earth, and Mars show how worlds receiving similar sunlight can develop very different environments. Proxima b receives a potentially temperate amount of energy, but its atmosphere remains unknown. Models suggest that stellar ultraviolet and X-ray radiation could gradually remove atmospheric gases. A strong stellar wind may also interact with the upper atmosphere and carry particles into space. The rate of this loss depends on conditions that have not yet been measured. A thick original atmosphere could leave enough gas after billions of years. Volcanic activity might replace part of what escapes. A planetary magnetic field could change how charged particles move around the world. Climate models also show that synchronous rotation does not automatically freeze one hemisphere and overheat the other. Even a moderately dense atmosphere can transport energy. Winds move warm air toward the night side and return cooler air toward the day side. Oceans could carry additional heat. Clouds may form beneath the fixed point where Proxima appears overhead. Bright cloud layers could reflect some incoming energy. On the dark side, ice might gather, while winds preserve milder regions nearer the boundary between day and night. Many outcomes remain possible. Proxima b could be dry and airless. It could hold a thin atmosphere. It could possess deep oceans, dense clouds, or conditions unlike any planet in the solar system. Present observations do not choose between these worlds. A visiting probe would search for atmospheric gases, reflected light, temperature patterns, and perhaps signs of clouds. Even limited measurements could transform broad possibilities into a clearer portrait. The habitable zone marks a place where a story may unfold. It does not write the story. Around the nearest star, one small planet remains wrapped in distance, holding its true climate quietly beyond the reach of present telescopes. A nearby planet can still disappear within the light of its star. Alpha Centauri is the closest neighboring star system, yet its planets remain extraordinarily difficult to observe. Distance is only one part of the problem. The stars themselves are bright, while the light reflected by a small planet is faint. A rocky planet does not usually create much visible light of its own. It reflects a small portion of the light falling upon it. Beside a sun-like star, the difference in brightness can reach billions to one. Detecting the planet resembles searching for a pale grain of dust beside a brilliant lamp viewed from many kilometers away. The apparent separation is also extremely narrow. Even if a planet follows an orbit similar to Earth's, the star and planet appear very close together from the solar system. Earth's atmosphere blurs incoming light. Telescope mirrors introduce tiny imperfections. These effects spread starlight across the image and can cover the much weaker planetary signal. Astronomers use several tools to reduce this glare. A coronagraph blocks part of the star's light inside a telescope. A star shade follows a different method. It would fly far in front of a space telescope and cast a carefully shaped shadow across the instrument, allowing nearby planets to appear more clearly. The edges of a star shade would resemble a large flower. Its petals are not decorative. Their exact shape controls how light bends around the structure. Instead of creating a simple circular diffraction pattern, the petals help form a deep and stable shadow. A visiting probe would observe the system from much closer range. Yet even there, bright stars could overwhelm sensitive cameras. Instruments would need protective shutters, careful exposure settings, and precise pointing. The probe might use a small coronagraph to examine regions close to each star. Infrared observations could provide another view. A planet warmed by its star emits heat, although the signal remains faint. Different wavelengths may reveal clouds, atmospheric gases, or changes between the planet's illuminated and dark hemispheres. The neighboring system is close enough to appear bright in Earth's sky, but its smaller worlds remain folded into that brightness. Around every distant sun, faint planets wait like quiet details hidden inside a field of light. A planetary transit requires a fortunate alignment. Thousands of exoplanets have been discovered when they pass in front of their stars. During a transit, the planet blocks a small portion of the star's light. Telescopes record a gentle dip in brightness. If that dip repeats at regular intervals, it can reveal the planet's orbital period. The method also provides an estimate of size. A larger planet hides more of the star and produces a deeper dip. When combined with mass measurements, this helps astronomers determine whether a planet is probably rocky, gaseous, or somewhere between. Yet most planets never transit from Earth's perspective. A planetary orbit is a thin plane in three-dimensional space. The plane must be aligned almost edge-on with the observer. A small tilt is enough to carry the planet above or below the visible face of the star. The closer a planet orbits, the greater its chance of transiting. This geometry partly explains why many known exoplanets have short years. They circle near their stars and pass in front more frequently. Wider orbits require longer observation and more exact alignment. A planet around Alpha Centauri A or B could therefore remain unseen by transit surveys, even if it were large and nearby by interstellar standards. Its orbit may simply be tilted away from the required angle. Other techniques can still reveal it. Radial velocity measurements search for the star's motion under the planet's gravitational pull. Astrometry measures tiny changes in the star's position across the sky. Direct imaging attempts to separate the planet's light from the surrounding glare. Each method finds a different part of the planetary population. Transits favor certain alignments. Radial velocity more easily detects massive planets near their stars. Direct imaging often favors large, warm planets on broad orbits. A spacecraft approaching Alpha Centauri would gradually escape many of these limitations. From a new viewing angle, an orbit that never transits from Earth might begin crossing the star. The changing perspective could reveal planets hidden from the solar system. Discovery depends not only on what exists, but also on where the observer happens to stand. A distant world may remain invisible for years, then quietly appear when space provides a different line of sight. Alpha Centauri A and B trace a long stretched orbit around one another. The two bright stars of Alpha Centauri are separated by a distance that constantly changes. Their mutual orbit is elliptical rather than circular. During their closest approach, the gap narrows to roughly the scale separating the Sun and Saturn. At their widest separation, the stars move several times farther apart. They complete one orbit in almost 80 years. A human lifetime is therefore similar to one full cycle of their celestial motion. During that interval, generations on Earth can watch the stars shift slowly around their shared center of gravity. Neither star remains fixed while the other circles it. Both respond to their common gravity. Alpha Centauri A is somewhat more massive, so it follows the smaller path. Alpha Centauri B travels around the same balance point along a wider curve. This shared point is called the barycenter. The Sun also moves around the solar system's barycenter as planets pull upon it, especially Jupiter. In a binary system, the effect is much larger and more visible. A spacecraft approaching Alpha Centauri must account for this movement. Its destination cannot be represented by one permanent coordinate. The future locations of both stars must be calculated for the year and day of arrival. The star's changing separation also shapes any planets around them. A planet close to Alpha Centauri A would mainly orbit that star. Alpha Centauri B would appear as a brilliant moving companion in its sky. Across decades, that second sun would brighten and fade as the stellar distance changed. From a planet near Alpha Centauri B, the other star could sometimes resemble a dazzling point of daylight. It might be bright enough to cast shadows during the local night, yet it would remain far too distant to appear as a broad solar disk. A probe passing between the stars would experience a changing gravitational landscape. Navigation calculations would combine the attraction of both suns. A course aimed too close to one star could be bent away from the desired path or accelerated into an unintended direction. From Earth, Alpha Centauri appears as one steady light. Within the system, that point opens into two moving suns, circling through a slow pattern nearly as long as a human life. Planets can maintain orderly paths inside a binary star system. Two stars do not automatically make stable planetary orbits impossible. The outcome depends on distance. A planet may orbit closely around one star, while the companion remains far enough away to provide only a gentle gravitational influence. This is known as an S-type orbit. Another possibility is a circumbinary orbit. In that arrangement, a planet travels around both stars together. The stars remain close to each other near the center, while the planet follows a much wider path. Several circumbinary planets have been discovered elsewhere in the galaxy. Alpha Centauri A and B are separated widely enough that stable regions may exist around each individual star. A planet staying relatively close to one member of the pair could complete regular orbits for very long periods. The distant companion would still disturb the path slightly, but not necessarily enough to remove the planet. Farther from the chosen star, the orbit becomes less secure. The gravity of the companion grows more influential. Over repeated cycles, small changes may accumulate. The planet's orbit could become increasingly elongated or tilted, eventually crossing an unstable region. Circumbinary planets around Alpha Centauri A and B would need to remain far outside the full motion of the stellar pair. A stable orbit would begin beyond a broad central zone. At such distances, the combined light from the stars would be weaker, and a planet would complete a long, slow year. Planet formation in a binary system presents additional questions. Young stars are surrounded by disks of gas and dust. A companion star can pull on the disk, truncate its outer region, and stir the material inside it. Collisions between growing planetary bodies may become faster and less gentle. Yet nature repeatedly creates planets in complicated environments. Some orbit binary stars, others belong to systems containing 3 or more suns. Planet formation appears capable of finding stable arrangements inside many different gravitational patterns. A spacecraft visiting Alpha Centauri could examine these regions directly. It might search close to each star and then look outward for wider worlds. Every orbit would reveal how matter settles beneath the influence of 2 suns. Binary systems are not scenes of constant disorder. Gravity can also create repeating pathways, allowing planets to drift for billions of years within the slow dance of their stars. The familiar constellations would gradually lose their shapes. Constellations appear almost unchanged across a human lifetime because the stars are extremely distant. Each star moves through the galaxy, but from Earth, their motions seem small. The patterns of Orion, Cassiopeia, and the Southern Cross remain recognizable from one generation to the next. An interstellar spacecraft changes its viewing position by trillions of kilometers. Nearby stars begin to shift against the more distant background. This effect is called parallax. Earth-based astronomers already use annual parallax to measure stellar distances as Earth moves from one side of the Sun to the other. During a voyage to Alpha Centauri, the baseline becomes far larger than Earth's orbit. The probe eventually observes the sky from several light-years away. Stars close to the solar system move noticeably from their familiar places, while distant stars shift much less. The Sun itself becomes part of the changing sky. At first, it remains overwhelmingly bright behind the spacecraft. As the journey continues, it shrinks toward the appearance of an ordinary star. The planets disappear into its light, long before the probe reaches the midpoint. From near Alpha Centauri, the Sun would shine as a bright yellow star. It would appear in the constellation Cassiopeia from that new perspective, adding another point to its familiar pattern. The solar system would no longer be a broad arrangement of planets. It would be hidden inside one distant speck. The spacecraft could use these shifting star positions to navigate. By comparing measured angles with a stored 3-dimensional map, it could estimate its location. Nearby stars would act like landmarks, moving across the sky in predictable ways as the probe advanced. The view ahead would also change. Alpha Centauri's stars would slowly separate from one another. Proxima would become distinguishable from the central pair. What began as one point would open into a wide system. Constellations are therefore not permanent designs placed upon a fixed sphere. They are temporary patterns created by one observing location. Move far enough, and the same stars form new shapes. Across the journey, the sky becomes a quiet record of distance. Familiar figures loosen, nearby lights drift apart, and the Sun settles gently among the other stars. Relativity begins to alter the journey before the spacecraft approaches light speed. At ordinary spacecraft velocities, the predictions of classical physics work extremely well. Time passes at almost the same rate aboard the spacecraft and on Earth. Distances behave as expected. The differences predicted by relativity remain far too small to matter. At a substantial fraction of light speed, those differences become measurable. According to special relativity, a moving clock runs more slowly when observed from a stationary frame. The travelers aboard a fast spacecraft would experience slightly less time than observers remaining on Earth. At 20% of light speed, the effect is present but modest. A journey measured as roughly 20 years from Earth would feel only several months shorter aboard the craft, depending on its acceleration and exact cruising speed. Relativity does not transform this voyage into an instant passage. At 90% of light speed, the difference becomes much greater. At still higher speeds, the traveler's experienced time could be far shorter than the time passing on Earth. Yet the energy required to continue accelerating rises dramatically as the spacecraft approaches light speed. An object with mass cannot be pushed to the speed of light using any finite amount of energy. Each increase becomes more demanding than the one before. Light itself travels at that limit because photons have no rest mass. Relativity also changes the appearance of the surrounding universe. Light arriving from ahead becomes shifted toward shorter wavelengths. Light from behind moves toward longer wavelengths. Stars appear concentrated toward the direction of travel through an effect called relativistic aberration. At 20% of light speed, these changes are noticeable to precise instruments, but not overwhelmingly large. At far higher speeds, visible light from ahead could shift toward ultraviolet wavelengths, while light from behind would soften toward infrared. The spacecraft's sensors and shielding would need to account for these changes. Navigation systems would translate distorted star positions back into a useful map. Cameras would adjust for altered colors and brightness. Even so, relativity does not offer an easy shortcut to Alpha Centauri at the speeds presently considered realistic. Its effects emerge gently at first, like a new layer of physics becoming visible as ordinary motion grows increasingly swift. Time and light remain familiar through most imagined journeys. Only as the spacecraft moves closer to nature's speed limit do they begin to reveal how flexible the universe has always been. A crude starship would need to become a nearly closed ecosystem. Robotic probes require electricity, temperature control, and occasional course corrections. Human travelers require something much larger. They need breathable air, clean water, food, safe temperatures, waste processing, and a stable atmosphere every hour of the journey. Space stations currently receive supplies and replacement components from Earth. An interstellar vessel would travel far beyond that possibility. Once it departed, no cargo craft could catch it. Almost every useful material would need to remain inside the system and circulate repeatedly. The International Space Station already demonstrates part of this process. Its environmental control systems collect moisture from cabin air and recover water from several waste streams. Other equipment removes carbon dioxide and produces oxygen through the electrolysis of water. The station recycles most of its water, but an interstellar vessel would need to approach a much more complete loop. Even a small daily loss becomes enormous when repeated across decades. A missing fraction of water may seem unimportant during 1 month. Across 50 years, it could become the difference between abundance and shortage. The atmosphere would also need constant attention. Humans release carbon dioxide, heat, humidity, skin cells, and trace gases. Plastics, electronics, plants, and cleaning materials add their own chemical compounds. Filters and processors must keep this enclosed air balanced without gradually allowing unwanted substances to accumulate. Waste would become a resource rather than something discarded. Water, carbon, nitrogen, phosphorus, and other elements would move through machines, plants, food, and people. A substance leaving one part of the habitat would become the raw material for another. Every pump, membrane, valve, and sensor would require maintenance. Spare components could be manufactured on board, but manufacturing also needs tools and materials. Biological systems may support mechanical systems, while machines protect the biology from sudden changes. The spacecraft would therefore carry more than passengers. It would carry a small artificial environment, preserving the same atoms through countless quiet cycles. Earth supports life through oceans, forests, soil, and air. A starship must fold a tiny version of that harmony into metal walls and carry it gently through the dark. Food would become part of the spacecraft's machinery. Stored food is practical for missions lasting months or a few years. It can be prepared on Earth, sealed carefully, and opened when needed. For an interstellar crossing lasting decades, stored meals alone become far less suitable. Food gradually changes even when preserved. Vitamins break down. Fats and proteins can lose quality. Packaging adds mass, and every meal produces material that must be reused or stored. A long voyage therefore encourages some form of onboard agriculture. Plants can perform several tasks at once. They transform carbon dioxide into oxygen through photosynthesis. They convert water, light, and nutrients into edible material. Their leaves release moisture that can be collected and purified. Their roots hold a living community of microbes that helps nutrients circulate. A starship garden would receive light from electric lamps rather than direct sunlight. The lamps would need to provide suitable wavelengths while producing as little wasted heat as possible. Water and nutrients could reach roots through hydroponic or aeroponic systems, avoiding the mass and complexity of ordinary soil. Crop selection would shape the habitat. Wheat, potatoes, soybeans, and other staple plants can provide calories. Leafy vegetables grow quickly and supply nutrients. Fruit-bearing plants add variety, but often require more space, time, and careful pollination. The garden must also survive disease. A fungus or bacterial infection spreading through one crop could affect the entire food system. Separate growing chambers, stored seeds, and genetic diversity would provide protection. Beneficial insects or carefully managed hand pollination might replace the broad ecological networks found on Earth. Plants produce material that humans cannot eat. Stems, roots, and damaged leaves still contain useful carbon and nutrients. Microbes, fungi, chemical processes, or small controlled ecosystems could break this matter down and return it to the growing system. Agriculture also demands human attention. Crops must be planted, inspected, harvested, and replanted across generations. Farming knowledge becomes as essential to the mission as navigation or propulsion. Inside a vessel surrounded by almost empty space, a green leaf would be more than decoration. It would be food, air, water, memory, and a small living component of the ship itself. Decades without gravity would slowly reshape the human body. Astronauts aboard an orbiting spacecraft appear weightless because the station and everything inside it are falling together around Earth. Without a floor continually supporting the body, muscles and bones receive less mechanical loading. The body adapts to this environment. Muscles used for standing and walking begin to weaken. Bones can lose mineral density. Fluids shift toward the upper body. The heart and blood vessels no longer work against gravity in the familiar way. Astronauts exercise for hours each day to reduce these changes. Resistance machines imitate weightlifting without ordinary weights. Treadmills and stationary bicycles help maintain cardiovascular strength. These measures are valuable, but they do not reproduce every effect of living under gravity. An interstellar crew might remain in space far longer than any human has before. Years of microgravity would raise questions that short missions cannot fully answer. Children developing aboard a multi-generational vessel would present an even deeper uncertainty. Human development has never been observed from birth to adulthood without a stable gravitational environment. A rotating habitat offers one possible solution. As the structure turns, objects inside tend to move toward the outer wall. The wall provides a supporting force that feels similar to gravity. Living quarters could line the inside of a large ring, with the apparent floor facing away from the central axis. The strength of this artificial gravity depends on the ring's radius and rotation rate. A small ring must spin quickly. Rapid rotation produces stronger differences between the head and feet and may cause disorienting Coriolis effects when a person moves. A larger structure can rotate more slowly while providing a similar downward force. Yet a wide ring adds mass, engineering complexity, and new stresses. Bearings, cables, seals, or rotating connections must operate reliably for many years. The central region could remain nearly weightless, offering a convenient place for storage or scientific work. Moving outward would gradually restore a sense of weight. A rotating starship would carry gravity not as a natural field, but as a carefully maintained motion. The habitat turns, the floor rises gently beneath each step, and an ancient earthly sensation follows its travelers toward another sun. Human travelers would require far more radiation shielding than machines. A robotic probe can use hardened electronics, redundant computers, and sacrificial components. Human tissue cannot be replaced so easily. Radiation can pass through cells, disturb molecules, and damage DNA. The effects depend on the particle, its energy, the tissue it crosses, and the length of exposure. Beyond Earth's atmosphere and magnetic field, two broad sources become important. Solar particle events release energetic particles from the sun, especially during periods of strong activity. Galactic cosmic rays arrive from beyond the solar system and include fast atomic nuclei produced by powerful events in the galaxy. A journey toward Alpha Centauri eventually passes beyond the heliosphere, but galactic cosmic rays remain. Their high energies make them difficult to stop. Simply placing a dense metal wall around the crew is not always ideal. Incoming particles can collide with heavy nuclei in the shielding and create showers of secondary radiation. Materials rich in hydrogen can perform better for many forms of space radiation. Water, polyethylene, food, and other hydrogen-containing supplies could be placed around living quarters. The same water needed for drinking and agriculture could form protective walls around sleeping areas. A central refuge might provide additional shelter. During periods of elevated radiation near a star, crew members could remain inside a compact region surrounded by water, supplies, equipment, and structural material. Magnetic or electric shielding has also been proposed. Strong fields could redirect some charged particles before they reached the hull. Creating a large protective field, however, requires power, superconducting magnets, cooling, and considerable mass. Neutral particles would not respond in the same way. Radiation exposure accumulates across time. A shielding system suitable for a short lunar journey may not be sufficient for several decades. Medical monitoring, protective medicines, and careful habitat design might all contribute, but none removes the environment completely. Shielding also competes with propulsion. Every added ton requires more energy to accelerate, and more energy to slow. The safest habitat may be too massive for the selected engine, while the lightest vehicle may provide too little protection. The space between stars looks clear and gentle, yet a crude vessel must carry an invisible shelter, wrapping its small human world in water, materials, and carefully arranged layers. Human hibernation remains a possibility rather than an available technology. Fiction often places interstellar travelers inside sleeping chambers. They close their eyes near Earth and awaken beneath another star. The passage seems to disappear between two brief moments of consciousness. Natural hibernation is more complex than ordinary sleep. Hibernating animals lower their metabolic rates. Their body temperatures, heart rates, and breathing patterns change. They reduce energy consumption while maintaining the ability to recover when the dormant period ends. Humans do not naturally enter the same state. Medicine can lower body temperature during certain procedures, and intensive care patients may remain sedated for extended periods. These conditions are not equivalent to years of controlled hibernation. Researchers study torpor in animals to understand how metabolism can be reduced safely. Space agencies have examined whether a human form of synthetic torpor could lower food, oxygen, water, and habitat requirements during long missions. Even a successful torpor system would require constant care. Machines would need to monitor circulation, breathing, temperature, nutrition, infection, and muscle condition. The crew could not simply be stored and forgotten. Medical equipment would become a continuous life support system within the larger spacecraft. Long inactivity also creates familiar complications. Muscles weaken when unused. Bones lose strength. Blood clots, pressure injuries, and infections become concerns. Natural hibernators possess biological adaptations that protect their tissues during dormancy. Humans may not share those protections. A rotating schedule might place part of the crew in torpor while others remained awake. The active group would maintain the habitat, monitor the sleeping travelers, and respond to faults. After several weeks or months, the groups could exchange roles. Torpor might reduce consumption during a journey to Mars. An interstellar crossing requires a far greater step. Maintaining a person safely for decades, then restoring full health, has never been demonstrated. For now, the sleeping starship remains an idea under study rather than a machine waiting to launch. The journey cannot yet be folded into one long night, and human time must still travel alongside the spacecraft. A slow interstellar voyage would become a moving civilization. A spacecraft traveling near 20% of light speed might reach Alpha Centauri within a few decades. A larger and slower human vessel could require centuries. In that case, the people arriving would not be the people who departed. A generation ship is a proposed spacecraft in which multiple human generations live and die during the voyage. The vessel begins as transportation, but soon becomes the only inhabited world known directly to its passengers. Its population must be large and diverse enough to remain healthy over time. Genetic planning, medicine, education, and social stability become part of the spacecraft's engineering. A failure of culture could be as important as a failure of machinery. Knowledge must pass from one generation to the next. Children would learn how to repair systems designed before they were born. They would study a destination they had never seen and a planet their grandparents remembered only through recordings. The mission's purpose might also change in meaning. The first crew chooses to leave Earth. Later generations inherit that choice. They may feel loyalty to the destination, curiosity about it, or attachment to the enclosed world that has always been home. Governance would need to survive centuries without outside authority. Rules must adapt to new conditions while preserving essential systems. Disagreements cannot be resolved by returning to Earth or forming a distant settlement elsewhere in the vessel. The habitat would need enough room for privacy, work, exercise, agriculture, celebration, and quiet retreat. Artificial landscapes, changing light cycles, gardens, and communal spaces could help create a richer environment than metal corridors alone. Population size must remain within the life support system's capacity. Too few people could reduce genetic and technical resilience. Too many could exceed food, water, and living space. Earths and resources would become closely connected across generations. By arrival, the starship may possess its own traditions, accents, stories, and calendar. Earth would be a bright historical star behind it. Alpha Centauri would be the destination written into every map, yet never visited by any living passenger. Such a ship would not merely transport a society, it would become one, a small human world moving quietly through the night between two larger worlds. The human mind would become part of the spacecraft's life support system. A long interstellar voyage would place a small group inside one enclosed environment. The same rooms, voices, routines, and mechanical sounds might remain present for years. There would be no walk outside, no distant town to visit, and no new landscape beyond the hull. Isolation does not affect every person in the same way. Some people value long periods of quiet. Others draw energy from frequent social contact. Even a carefully selected crew may experience changing moods, interrupted sleep, reduced concentration, or disagreements during a long mission. Space agencies already study these effects through isolated habitats and simulation missions. Crews live together in confined facilities, while researchers observe communication, teamwork, workload, sleep, and decision-making. These experiments help identify designs and habits that support stable performance. Privacy becomes especially important. A crew member may need a small room with a door, personal objects, and time away from communal activity. Shared spaces are also necessary. Meals, exercise, celebrations, and scientific work give the group a steady social rhythm. Lighting would help preserve the body's daily cycle. Bright, cool light could support wakefulness during working hours. Softer light would signal the approach of rest. Plants, changing images, music, and recorded natural sounds could reduce the sameness of the enclosed environment. Windows may offer another form of relief. During most of the journey, the view would contain dark space and distant stars. Yet even a simple visual connection with the outside universe could soften the feeling of confinement. Digital windows might display forests, oceans, weather, or familiar skies from Earth. The crew would also need ways to resolve tension before small concerns became lasting divisions. Training could include shared decision-making, conflict management, and recognition of behavioral changes. Psychological care would be partly delivered by the crew itself. Propulsion carries the habitat forward, but cooperation keeps it inhabited. Across the quiet distance, human patience becomes as necessary as oxygen, water, and warmth. Earth's voice would always arrive from an earlier time. Near the International Space Station, astronauts can speak with people on Earth almost immediately. Conversations may contain brief delays, but they still feel natural. Questions receive answers. Families can share news while it remains recent. Near Alpha Centauri, each message would take more than 4 years to cross the distance. A reply would require another 4 years to return. No ordinary conversation could continue across such a gap. A message received by the spacecraft would describe an Earth that had already changed. Children would be older. Scientific projects would have advanced. Buildings, governments, and communities might no longer look the same. The people speaking in a recording could have entered entirely different stages of life before their words reached the ship. The crew's own messages would become similar time capsules. A report sent during departure might arrive after the vessel had traveled far beyond the outer solar system. Earth would receive descriptions of events that the crew had already remembered for years. Communication would remain valuable, but its purpose would change. Earth could send scientific updates, cultural archives, engineering advice, books, films, and messages from families. The spacecraft could return observations and records of life aboard the mission. Each side would speak without expecting an immediate response. Psychological support could not depend on a live counselor on Earth. The crew would need trained members, private support systems, and onboard software able to guide reflection or recognize signs of strain. Recorded messages from loved ones might remain comforting, even as their age became increasingly clear. A generation ship would experience an even greater separation. Later passengers might receive recordings made before their births. Earth would become a place known through history, delayed broadcasts, and a small yellow star behind the vessel. The communication beam would never truly break. Light would continue carrying voices in both directions. Yet the messages would pass one another like letters between distant centuries, preserving connection without preserving the present. medical care would have to function without a hospital beyond the hull. Present astronauts receive extensive support from physicians on Earth. Crew members can describe symptoms, transmit measurements, and perform examinations under remote guidance. In an emergency aboard the International Space Station, returning to Earth may also remain possible. An interstellar crew would have no rapid return. A medical question sent from Alpha Centauri would require years to reach a physician on Earth. The answer would arrive years later. Diagnosis and treatment must therefore occur inside the spacecraft. At least some crew members would need broad medical training. They might perform dentistry, wound care, imaging, laboratory testing, and minor surgery. A small team would need skills that are normally divided among many specialists. Portable ultrasound could become especially useful. It contains no large magnet and creates no ionizing radiation. Ultrasound can examine muscles, organs, blood vessels, and developing pregnancies. Software might guide the operator by showing where to place the probe and how to interpret the image. Automated medical systems could compare symptoms with stored records. They might recommend tests, identify dangerous patterns, and explain procedures step by step. The final decisions would remain connected to trained human judgment, especially when information was incomplete. Equipment must also be repairable. A broken scanner could not be replaced through resupply. Components might follow standardized designs so that parts could be exchanged between devices. Additive manufacturing could produce simple tools, braces, dental items, and replacement housings. Blood products and biological materials are more complicated. They require careful storage and often remain useful for limited periods. Future biotechnology might allow some medicines, tissues, or therapeutic proteins to be produced on board. The medical system would also provide preventive care. Exercise, clean air, balanced food, vaccination, sanitation, and regular examinations could reduce the number of emergencies. A crewed starship cannot carry an entire hospital. It must instead carry knowledge, adaptable tools, and the ability to turn one small room into many kinds of clinic. A starship pharmacy would slowly change as it crossed the dark. Medicines do not remain unchanged forever. Their active ingredients may gradually break down. Heat, moisture, radiation, and imperfect storage can affect their stability. Packaging can also age, allowing small amounts of gas or water to enter. Many medicines used on Earth have labeled shelf lives measured in years rather than decades. An interstellar journey could last much longer. A supply packed before departure might therefore become less reliable before the spacecraft approached its destination. The problem is not solved by carrying greater quantities. Additional medicines add mass and require controlled storage. Some drugs need refrigeration, others are sensitive to light or radiation. A larger collection also creates more items that must be inspected and replaced. The spacecraft could store medicines inside a shielded, temperature-controlled region. Sensors would track each container's history. Small laboratory instruments could test chemical purity rather than relying only on the printed expiration date. Some treatments might be stored as stable ingredients rather than finished tablets or liquids. An onboard pharmacy could combine those ingredients when needed. Automated equipment might adjust doses for age, body mass, medical condition, and changes caused by long residence in space. Biological manufacturing offers another possibility. Engineered microbes or cultured cells can produce certain proteins and medical compounds. A compact bioreactor might create fresh material from stored genetic instructions and simple nutrients. The resulting product would still require purification and careful testing. Manufacturing every medicine would be unrealistic. The crew would need to choose which conditions could be treated and which production systems offered the greatest value. Broad-use antibiotics, pain relief, anesthetics, allergy treatments, and emergency medicines would receive careful attention. Medical knowledge could also change during the journey. Earth might discover better treatments and transmit their formulas. The message would arrive years later, but a flexible manufacturing system could still turn information into a physical medicine. A starship pharmacy would not be a silent cupboard of bottles. It would be a small laboratory, preserving the ability to rebuild useful treatments as old supplies gently faded. The destination may be understood differently by the time the spacecraft arrives. An interstellar mission would be planned using the best observations available at launch. Astronomers would estimate planetary masses, orbital periods, temperatures, and atmospheric possibilities. Yet much of the system could remain unseen. A rocky planet may hide within the glare of its star. Another world may follow an orbit requiring decades to measure accurately. Small planets may produce signals close to the limits of an instrument. Stellar activity can imitate or obscure the motion caused by an orbiting world. During a voyage lasting 20, 50, or 100 years, astronomy on Earth would continue. Larger telescopes could begin operating. New methods might separate planetary light from starlight. Observations could reveal additional planets, rings, dust belts, moons, or unexpected patterns in the system. Updates could be transmitted to the spacecraft. Because the signals travel at light speed, they would eventually overtake a slower probe. The onboard map might therefore change several times during the journey. A newly discovered planet could become the preferred target. The craft might make a small early adjustment, shifting its path across the remaining distance. A change made many years before arrival could move the final encounter by millions of kilometers. Late discoveries would be harder to use. A probe traveling at a large fraction of light speed cannot easily turn. Its instruments could still observe a newly identified world from a distance, but the vehicle might be unable to pass nearby. The destination itself would also continue changing. Planets would move along their orbits, storms could form and disappear, stellar flares would rise and fade. An atmosphere observed from Earth decades earlier might look different during the encounter. No mission can arrive at a perfectly frozen prediction. It reaches a real system that has continued living while the spacecraft crossed the gap. The map prepared at departure is therefore not the destination. It is a quiet first sketch, refined by new light until the neighboring stars finally reveal themselves. A visiting spacecraft must avoid confusing Earth life with life from another world. Spacecraft built on Earth carry traces of Earth. Microbes can survive in clean rooms, beneath protective layers, and inside tiny spaces between components. Most are harmless parts of the planet's natural biological community. When missions visit potentially habitable environments, contamination becomes scientifically important. Earth organisms could alter the destination. They could also create a misleading result. A future instrument might detect biological material without knowing whether it originated there or arrived aboard an earlier spacecraft. Planetary protection practices reduce this possibility. Spacecraft can be assembled in controlled facilities. Surfaces may be cleaned with heat, chemicals, radiation, or other methods. Mission paths can also be designed to avoid an unintended impact. An interstellar flyby would present less contamination risk than a lander. The probe could pass through the system without touching a planet. An orbiter would require greater care because a later failure might eventually send it toward the surface. A lander intended for a potentially habitable exoplanet would raise questions far beyond current missions. It may have traveled for decades while dormant organisms remained inside protected cavities. Sterilizing such a machine completely, while preserving delicate electronics, would be extremely difficult. The same principle applies in the opposite direction. Samples from another biosphere could require isolation before entering a human habitat. Their chemistry might be harmless, or it might interact with Earth-derived biology in unexpected ways. Careful study would begin inside sealed instruments. Present planetary protection rules are designed for solar system missions. An interstellar mission would require new policies, but the central purpose would remain familiar: preserve the environment and protect the meaning of the science. The first evidence of distant life should not be a fingerprint carried from the launch site. A careful spacecraft arrives as quietly as possible, observing another world without immediately adding Earth to its story. An interstellar spacecraft may need to be built far above Earth. Large spacecraft begin their lives on the ground because Earth holds factories, workers, and established supply chains. Yet launching an entire interstellar vehicle from the surface would create severe limitations. Every component must survive vibration, atmospheric pressure, and the narrow shape of a rocket fairing. The spacecraft may also be too massive for a single launch. Thick shielding, large radiators, powerful engines, fuel tanks, communication equipment, and scientific instruments could require many separate missions. The pieces would rise gradually and meet in orbit. Assembly could take place near Earth, around the Moon, or at a more distant construction site. Robotic arms would join structural sections. Automated vehicles would deliver tanks, cables, and protective layers. Human crews might supervise the early stages while remaining close enough to return home. Building in space allows structures to unfold beyond the limits of a launch vehicle. A magnetic sail could span many kilometers. A laser sail might remain extremely thin while covering a broad area. Rotating habitats could be assembled as wide rings rather than compact shapes folded inside rockets. Materials may also come from beyond Earth. Water from the moon or asteroids could become shielding, propellant, or life support reserves. Metals extracted from small bodies might reduce the amount lifted through Earth's gravity. These industries do not yet operate at the required scale, but they could grow through many smaller missions. The construction site must remain carefully organized. Tiny pieces of debris can damage equipment moving at orbital speed. Every released bolt, fragment, and tool must be controlled. The completed craft would undergo repeated inspection before its departure. A propulsion system using nuclear reactions or immense laser energy might also require separation from populated regions. Final testing could occur far from Earth, where an unexpected failure would create less danger for satellites and communities. The mission would therefore begin long before the interstellar engine awakened. It would start with launches, rendezvous, quiet assembly, and years of patient preparation in the space surrounding Earth. The first starship may not rise from a launch pad as one complete machine. It may take shape slowly above the atmosphere, piece by piece, beneath the steady light of home. The outer solar system could become a proving ground for interstellar machines. A spacecraft intended to operate for decades cannot be tested fully during a short mission near Earth. Its components must experience cold, radiation, distance, and long communication delays. The outer solar system provides a natural place to practice. A precursor vehicle could travel beyond Neptune while testing propulsion, navigation, power generation, and autonomous repair. The journey would remain far shorter than a voyage to Alpha Centauri, yet it would expose the craft to years of deep space operation. Long-distance communication could be practiced as the signal weakened. The spacecraft might compress images, choose transmission schedules, and aim a narrow laser toward Earth. Ground stations would learn how to recover faint data from a moving source. Hibernation systems could also receive genuine trials. The probe might sleep for months, awaken without assistance, inspect itself, and return to dormancy. Each successful cycle would increase confidence that a later machine could repeat the process across decades. A test craft could deliberately operate with reduced contact. Engineers might send only broad goals, rather than detailed instructions. The onboard computer would plan observations and respond to minor failures. Earth would remain available, but the spacecraft would practice behaving as though help were years away. Propulsion experiments could occur beyond crowded orbital regions. Electric engines, nuclear systems, sails, or magnetic braking devices might be tested against the solar wind. Their performance would reveal whether theoretical calculations remain accurate outside laboratories. The craft could also study the heliopause, where the sun's influence meets interstellar space. Voyager 1 and Voyager 2 crossed this boundary, but future probes could carry more sensitive instruments and follow carefully chosen directions. A precursor mission would still produce valuable science even if its technology remained incomplete. It could examine distant planets, small icy bodies, magnetic fields, and the particles surrounding the solar system. Interstellar engineering would therefore grow through gradual experience. Each machine would travel farther, sleep longer, and decide more for itself than the one before. Before a spacecraft crosses 4 light-years, smaller travelers may first teach it how to cross the quiet edge of the sun. Scout probes could examine the road before a larger mission departs. The route toward Alpha Centauri appears empty from Earth, but its exact conditions are not perfectly known. Astronomers estimate the average amount of interstellar gas and dust. They study nearby clouds and measure how starlight changes while passing through them. A spacecraft, however, follows one narrow path. Small precursor probes could travel ahead of a larger vehicle. They would measure particle density, magnetic fields, radiation, and the distribution of dust. Their observations could reveal whether one route offers slightly calmer conditions than another. These scouts would not need to reach the destination first. Even measurements collected within the outer solar system and nearby interstellar medium could improve shield designs. Engineers would learn how particles behave against moving surfaces and how instruments age beyond the heliosphere. A probe could carry a dust detector made from thin films or sensitive electrical grids. When a particle passed through, it would create a tiny signal. Repeated measurements would build a map of particle sizes and directions. Magnetometers would study the faint interstellar magnetic field. Plasma instruments would count charged particles. Radiation detectors would record energetic nuclei arriving from the galaxy. Together, these instruments would describe a region usually inferred only from distant observations. A network of scouts could spread across several directions. One would travel toward Alpha Centauri. Others would explore neighboring paths. Differences between their measurements would show whether the local interstellar environment contains small clouds, boundaries, or streams. The larger mission might then adjust its route slightly. A change of only a tiny angle near the Sun produces a wide separation after several light years. The craft could avoid a denser region without adding an enormous distance. Scout probes could also serve as communication markers. They might test relay methods, navigation beacons, or optical links across gradually increasing distances. Their usefulness would depend on power and survival. But even temporary relays would teach engineers how signals behave. No map of space is ever complete. Yet each precursor adds another measured line across the unknown. Long before the main craft arrives, small scouts may drift ahead like quiet lanterns, measuring the darkness one particle at a time. A swarm of probes can succeed without every member surviving. Traditional space missions often place years of work inside one spacecraft. If a major component fails, the scientific return can be greatly reduced. An interstellar mission may follow another approach by sending many smaller probes together. Each probe could carry a simple set of instruments. Some might focus on imaging. Others could measure magnetic fields, dust, plasma, or stellar radiation. A few might carry stronger transmitters and help return information from the others. The probes would not need to remain close. During the crossing, small differences in speed and direction would spread them across a wide formation. This separation could become useful near the destination. One probe might pass close to Proxima b, another could observe Proxima Centauri itself. Others might continue toward Alpha Centauri A and B. The mission would exchange one carefully controlled path for many overlapping paths through the system. A swarm also provides several viewing angles. Planetary atmospheres change as light passes through them from different directions. Clouds rotate. Illuminated hemispheres turn toward and away from each probe. Several brief observations could combine into a richer picture. Failures would remain expected. A sail might tear during acceleration. A computer could stop responding after years of radiation exposure. A probe might pass too far from its target. The mission could still continue through the surviving members. The probes may share information with one another before transmitting to Earth. Nearby craft could combine measurements or send data toward a probe carrying a larger antenna. Coordinating at interstellar distance would require precise clocks and autonomous software. Manufacturing many probes could also improve quality. Repeated production reveals weaknesses that remain hidden in a single custom spacecraft. Each unit may become simpler and more reliable because the design is built many times. A swarm does not remove the need for careful engineering. It changes the meaning of success. The mission no longer depends on every machine completing every task. It depends on enough machines carrying fragments of the same scientific purpose. Across the neighboring system, the probes would scatter like seeds of observation. Each follows a separate path, while their combined light returns one shared image of another sun. The long crossing can become a scientific mission of its own. Most of the journey to Alpha Centauri takes place far from planets and stars. This region may appear uneventful, but it offers access to an environment difficult to study from inside the solar system. The Sun produces a stream of charged particles called the solar wind. This wind creates a vast bubble known as the heliosphere. Earth and the planets move within it. Beyond its outer boundary lies the local interstellar medium. Voyager 1 and Voyager 2 have entered this region and continue returning measurements. They detect changes in plasma, magnetic fields, and cosmic rays. Their instruments were designed decades ago, and some have gradually been switched off as electrical power declines. A purpose-built interstellar craft could carry newer and more sensitive equipment. It would measure how the Sun's influence fades along the exact direction of Alpha Centauri. It could study the shape of the heliosphere and compare the region ahead with those explored by the Voyagers. Farther outward, the probe could examine interstellar gas directly. Hydrogen and helium atoms drift through the local galactic neighborhood. Small amounts of heavier elements and dust carry material created by earlier generations of stars. The craft might collect a few particles inside protected instruments. Their composition would reveal how matter has mixed through the Milky Way. Isotopes could preserve traces of stellar explosions, ancient winds, and the slow recycling of material between stars. The journey would also provide a long baseline for astronomy. Telescopes carried far from the sun could observe distant objects from a changing position. Combined with observations from Earth, this baseline would improve measurements of distance and motion. A probe could look backward as well. The solar system would become a distant planetary system, allowing scientists to test how Earth and the other planets appear when their light blends together. These observations would improve methods used to study exoplanets. The crossing would not be a scientific pause between departure and arrival. It would be a continuous passage through a region humanity has barely sampled. Between the stars, even empty space contains history. Gas, dust, light, and magnetic fields carry the faint memory of the galaxy through which the spacecraft quietly moves. A close flyby could separate the light of an alien atmosphere. A planet's atmosphere changes the light passing through or reflecting from it. Certain gases absorb specific wavelengths. When astronomers spread the light into a spectrum, these missing regions appear as lines or bands. From Earth, obtaining such a spectrum from a small planet near Alpha Centauri would be extremely difficult. The planet's signal is faint, and the nearby star overwhelms it. A visiting probe would observe from a far shorter distance. During the approach, the spacecraft could measure how the planet's brightness changes across its orbit. Reflected light may reveal clouds, oceans, ice, deserts, or haze. Different surfaces reflect different combinations of visible and infrared wavelengths. If the probe passed behind the planet relative to its star, it could measure thermal emission from the night side. If the planet crossed in front of the star from the probe's viewpoint, starlight might filter through the edge of the atmosphere. The resulting spectrum could contain signs of water vapor, carbon dioxide, methane, oxygen, or other molecules. No single gas would automatically demonstrate biology. Each must be interpreted alongside temperature, geology, stellar activity, and the presence of other gases. Clouds could hide lower atmospheric layers. Haze could scatter light and soften spectral details. A thin atmosphere might produce only a faint signal during the brief encounter. The probe would need extremely sensitive detectors and stable pointing. Polarized light offers another clue. Reflection from clouds, particles, or a liquid surface changes the orientation of light waves. Measuring this polarization could help distinguish between possible landscapes. The spacecraft might never form a detailed photograph resembling a globe. The planet could remain only a few pixels across, yet each pixel would contain carefully separated colors, temperatures, and changing patterns. A small spectrum can reveal more than a sharp image. It can describe air, weather, chemistry, and the movement of heat around a distant world. After crossing trillions of kilometers, the probe may meet another planet not as a landscape, but as a quiet ribbon of light carrying the signature of its sky. A sail may use the destination star itself as a brake. A spacecraft accelerated by a laser near Earth does not carry a large engine. This greatly reduces its mass. Yet it also leaves the vehicle without an obvious way to slow when Alpha Centauri finally approaches. One possible solution uses the light and gravity of the stars ahead. A broad reflective sail could approach Alpha Centauri, at a carefully calculated angle. Photons striking the sail would apply a small but continuous pressure. The star's gravity would bend the spacecraft's path at the same time. Together, these forces might reduce the craft's speed and redirect it deeper into the system. The probe could then aim toward Alpha Centauri b, or perhaps continue toward Proxima Centauri. This method is sometimes called photogravitational assistance. It resembles a gravitational flyby, but adds the pressure of starlight acting upon a sail. The spacecraft exchanges no propellant. It interacts instead with the natural environment of the destination. The maneuver would demand extraordinary precision. The sail must remain folded or protected during decades of travel. It must deploy correctly as the star grows brighter. Its surface must survive intense heating without warping, tearing, or absorbing too much energy. The approach angle would need to be determined long before arrival. A small error could carry the craft too far from the star, producing too little braking. A course passing too close could expose the sail to excessive heat or bend the trajectory in an unwanted direction. The sail must also face the star while keeping instruments protected. Its orientation may change continuously as gravity turns the path. Autonomous navigation would compare measured starlight with stored predictions and make gentle adjustments. The maneuver could last only a short time compared with the entire mission. Years of quiet travel would lead to a carefully choreographed passage near one brilliant sun. The destination would therefore provide more than a place to visit. Its light could become the final part of the propulsion system, catching the arriving sail and softly removing the speed gained beside another star. The nearest planetary system may not contain a welcoming destination. Alpha Centauri attracts attention because it is close. Proxima b attracts attention because it has a mass similar to Earth and circles within a potentially temperate region. These facts make the system scientifically valuable, but they do not promise familiar conditions. Proxima b may possess a substantial atmosphere, or it may have lost much of its gas. Its surface could hold water, dry rock, thick ice, deep clouds or landscapes unlike anything in the solar system. The star's repeated flares may shape the planet's atmosphere and chemistry. Planets may also orbit Alpha Centauri A and B, although the present picture remains incomplete. Some early signals have later disappeared under closer analysis. Stellar motion, instrumental effects, and limited observations can imitate planetary patterns. By the time an interstellar probe is ready, telescopes may provide a much clearer map. They might reveal an Earth-sized world around one of the brighter stars. They could also show that the most promising targets are airless, cloud-covered, or absent entirely. The mission would remain worthwhile. A system does not need a second Earth to contain important science. A lifeless rocky planet could reveal how worlds form inside a binary system. An atmosphere altered by a red dwarf could explain whether such planets commonly retain air. A barren system would also carry meaning. It would show that planetary habitability depends on more than size and temperature. It might help astronomers recognize which nearby stars deserve later attention. The spacecraft must therefore be designed around questions rather than expectations. Instruments should examine stars, planets, dust, magnetic fields, and atmospheres. The mission cannot depend on discovering one particular kind of world. Traveling to the nearest stars is not the same as traveling toward a promised home. It is an act of measurement, carried across a distance where nature has made no promise about what waits. The return data may continue arriving long after the encounter ends. During a fast flyby, the spacecraft could collect more information than it can immediately transmit. Cameras may produce images. Spectrometers may record thousands of measurements. Dust detectors, magnetometers, and radiation instruments could operate simultaneously. The probe would store these observations in onboard memory. After leaving the system, it would begin sending them toward Earth. The transmission rate might remain extremely low because of limited power and the enormous communication distance. Important information could be sent first. A navigation image confirming a successful encounter might receive the highest priority. Basic planetary measurements could follow. Large images and detailed spectra might be divided into smaller packets transmitted over months or years. The spacecraft could send several copies of the most valuable data. Earth-based receivers would compare them and correct errors. Less important information might be sent only once to conserve energy. As the probe continued away from Alpha Centauri, the signal would weaken. The transmitter's power source would also decline. Engineers would need to choose how long the communications phase could continue. Receivers on Earth may improve during the voyage. Telescopes and detector arrays built decades after launch could gather signals more efficiently than the systems imagined by the original mission designers. The spacecraft would speak with old hardware, while Earth listened with newer ears. The probe might never receive confirmation that its data arrived. A message from Earth would need more than 4 years to reach it. By then, the spacecraft would be much farther away, and perhaps already operating with very little power. Its task would remain simple: transmit each packet, point toward the distant sun, preserve the remaining energy, continue until the final useful signal leaves the antenna. The scientific encounter may last only hours, but its return can unfold across years. On Earth, another world could reveal itself slowly, one patient fragment of data at a time. An interstellar mission must survive changes on Earth, as well as changes in space. A voyage lasting several decades crosses more than physical distance. It also crosses scientific, political, and cultural time. The organizations that approve the mission may change names, funding systems may be reorganized, engineers may retire long before the spacecraft reaches its target. Knowledge must therefore pass between generations of mission teams. Technical documents must remain readable. Software formats must be preserved or converted. New engineers must understand why decisions were made many years earlier. Long missions already face this challenge. Voyager has operated since 1977. Many people now supporting the spacecraft were not part of its construction. They work with systems designed under older assumptions, using carefully preserved records and knowledge passed from earlier teams. An Alpha Centauri mission would extend this pattern much further. The people receiving its first close observations might not yet be born when the probe leaves Earth. Ground equipment would also evolve. The original computers may disappear. Communication standards may change. Receiving stations may be rebuilt. The project must remain compatible with technologies that cannot be predicted in detail. International cooperation could provide stability. Observatories in several countries might listen for the probe. Scientific archives could be duplicated across institutions. No single organization would hold the only copy of the spacecraft's design or communication protocol. The mission may also become a cultural object. Its progress would be followed through schools, museums, public archives, and annual observations. Each generation would inherit the responsibility of listening for a machine launched by the one before it. This continuity is a form of engineering. The spacecraft needs durable materials, but Earth needs durable memory. A forgotten frequency or lost decoding method could silence an otherwise successful mission. The journey therefore connects people who never meet. One generation constructs the craft, another guides its middle years. A later one receives the light gathered beneath a neighboring sun. Stars move closer and farther apart across deep time. Alpha Centauri is called the nearest star system because of its present distance. This arrangement is not permanent. Every star follows its own orbit through the Milky Way, moving under the combined gravity of the galaxy. The Sun travels as well. It carries the planets through space while circling the galactic center. Nearby stars approach from different directions and later recede. Over tens of thousands of years, the list of the Sun's nearest neighbors changes. Alpha Centauri is currently moving closer to the solar system. It will continue approaching for many thousands of years before beginning to recede again. The change is meaningful on an astronomical scale, but too slow to simplify any mission being planned today. Other stars will eventually pass nearer. The small star Gliese 710 is expected to move through the distant region of the Sun's comet cloud far in the future. It may briefly become one of the closest stellar neighbors, although humanity's circumstances by then cannot be predicted. These motions show that interstellar distance is not a fixed arrangement drawn permanently across the galaxy. The local stellar neighborhood behaves like a slow stream. Stars pass one another while remaining separated by enormous gaps. A spacecraft crossing toward Alpha Centauri would participate in this motion. Its course would be calculated not toward a stationary point, but toward a meeting place between moving objects. The same principle extends across the entire Milky Way. Constellations gradually change. Stellar groups spread apart. Some stars pass near one another and exchange comets. Others continue through the galaxy without close encounters. Human history occupies such a small interval that the sky appears fixed. On longer timescales, it becomes fluid. The nearest star is therefore not an eternal address. It is the closest light during one chapter of the Sun's long galactic journey, drifting nearby before the stars slowly move apart again. Seeing the solar system from outside would transform the search for other Earths. A probe traveling toward Alpha Centauri would eventually look back and see the Sun as another star. Earth would no longer appear as a broad world. It would become a tiny point mixed with the light of the other planets. This distant view would be scientifically valuable. Astronomers searching for life on exoplanets face the same limitation. They usually observe unresolved points rather than detailed landscapes. By studying Earth from interstellar distances, researchers could test which signs of a living planet remain visible. Earth's brightness changes as it rotates. Oceans, continents, clouds, ice, and deserts reflect different amounts of light. A distant instrument may detect subtle color variations as these features move across the illuminated hemisphere. The atmosphere leaves its own spectral patterns. Oxygen, water vapor, carbon dioxide, methane, and ozone absorb particular wavelengths. Some of these gases are connected to life, but geological and chemical processes can also create misleading signals. The solar system provides a controlled comparison. Venus has a thick carbon dioxide atmosphere and bright clouds. Mars has a thin atmosphere and a dry surface. Jupiter and Saturn contain very different gases. Viewed together, these worlds show how varied planetary spectra can become. The probe could observe the solar system while gradually increasing its distance. Scientists would compare its measurements with the detailed knowledge already available from nearby missions. This would reveal which features survive when a complex planetary system becomes a few faint points. The results could improve the design of telescopes searching around other stars. They would help astronomers distinguish clouds from surfaces and biological signals from non-living chemistry. An interstellar mission would therefore begin studying distant worlds before reaching one. By turning backward, it would transform Earth into an exoplanet and the Sun into a distant stellar system. From far enough away, home becomes part of the same mystery humanity has always searched for among the stars. The first journey to Alpha Centauri will probably be made by something very small. Human imagination often pictures a vast starship carrying explorers toward another sun. Such a vessel would require propulsion, shielding, food, artificial gravity, medicine, and a nearly complete living ecosystem. Its mass would make acceleration extraordinarily difficult. A robotic probe can be much lighter. It does not require air, water, or living space. It can endure stronger acceleration. It can sleep for years and accept a brief encounter as the conclusion of its journey. The earliest successful mission may therefore be a wafer-scale spacecraft, a small sail, or a compact probe assembled with extreme care. It may weigh grams rather than tons. Its cameras may fit inside a device smaller than many present satellites. Several probes could launch together. They would leave the solar system as a scattered fleet, each carrying a small portion of the mission. Decades later, the surviving craft would cross the neighboring system and send their measurements home. Their images might not resemble the sweeping scenes imagined in fiction. A planet could occupy only a few pixels. A star might appear as a bright disk surrounded by instrumental glare. Yet those measurements would come from inside another stellar system. This first crossing would not immediately create a route for human settlement. It would demonstrate navigation, communication, shielding, autonomy, and survival across several light years. Later missions could build upon each lesson. The machine itself may be almost invisible. From Earth, no telescope would watch it moving through the darkness. Most of its life would pass in silence between occasional transmissions. Yet scale does not determine significance. A small instrument can carry a civilization's curiosity farther than any living traveler has gone. The first visitor to another star may not resemble a ship at all. It may be a thin sail, a patient computer, and a tiny camera drifting toward a light that humans have watched since ancient nights. The journey to Alpha Centauri reveals how wide the nearest distance truly is. The destination lies beside the solar system on maps of the galaxy. Its light reaches Earth in only a little more than 4 years. Yet every stage of the crossing unfolds beyond ordinary experience. The spacecraft must gather enormous speed, survive radiation and dust, navigate without immediate guidance, and preserve power through years of darkness. It must find a moving destination and collect its observations during a brief encounter. A larger vessel must carry air, water, food, medicine, gravity, shielding, and a functioning society. It must preserve not only machinery, but memory and purpose across generations. None of these challenges changes the laws of nature. No unknown barrier stands between the Sun and Alpha Centauri. The difficulty comes from ordinary physics applied across an extraordinary distance. Small amounts of dust matter because the spacecraft moves so quickly. Small navigation errors matter because the path is so long. Small losses of air or water matter because the journey may last decades. The destination remains quietly present throughout these calculations. Alpha Centauri A and B continue circling one another. Proxima glows faintly beyond them. Their planets follow paths still only partly known. Every proposed sail, fusion engine, shield, clock, and autonomous computer is an attempt to connect those distant motions with the small world where the journey begins. The first mission may fail. Later attempts may travel farther. Knowledge will accumulate through tests, precursor probes, and patient observations. Interstellar travel may grow not from one sudden invention, but from many technologies becoming reliable together. The nearest stars are not unreachable because they are hidden. They are difficult precisely because they can be seen. Their light arrives easily, while matter must cross every kilometer between them. And within that difference lies the quiet scale of the universe. Light touches the neighboring stars in years, while a spacecraft must learn how to endure the entire road. The nearest star system is wider, stranger, and more intricate than a point of light in the night sky. It contains 3 moving suns, possible rocky planets, changing magnetic weather, and enormous spaces between its separate regions. Reaching it asks for speed, patience, energy, protection, and an extraordinary trust in machines operating far from home. Yet the difficulty does not diminish the wonder. It reveals how carefully the universe holds its distances. Even neighboring stars are given room to shine within their own deep and quiet darkness. But for now, there is no need to travel any farther. Let the imagined spacecraft continue without attention. Let its sail grow smaller against the stars. Let the distant sun soften behind it until it becomes one calm point among many. There is nothing more to calculate tonight. The engines may fall silent, the instruments may rest. The long spaces between the stars can remain empty, gentle, and still. Let the shoulders settle a little more deeply. Let the muscles of the face soften. Let each breath become slower than the one before it. The journey can continue without effort. Alpha Centauri has waited for billions of years. It will remain there beyond this night, carrying its 3 quiet lights through the galaxy. And if wakefulness remains for a little longer, another quiet journey is waiting on screen, ready to drift toward a different corner of the universe. If these calm nights bring a little peace, there is always a place here to return. The stars will keep moving gently, and Nightfall science will be here to follow them, one drifting mind at a time. Sleep well, and good night.